site of human activity for 15,000 years. This land is the territory of the Huron-Wendat and Twin First Nations, the Seneca, and most recently the Mississaugas of the Credit River. The territory was the subject of the Dish with One Spoon Dwellings Belt Covenant, an agreement between the Iroquois Confederacy and the Confederacy of the Ojibwe and allied nations to peaceably share and care for the resources around the Great Lakes. Today, the meeting place of Toronto is still the home to many Indigenous people from across Turtle Island, and we are grateful to have the opportunity to work in the community on this territory. So thank you everyone for coming out tonight and welcome to AstroTours. My name is Elisa Obertus and I'm one of the co-directors of AstroTours. If this is your first time coming out to one of our events, we are a monthly event. We usually run the first Thursday of every month, where we have usually graduate students giving public talks, public audiences, talks related to the research and the things that they do here at the University of Toronto. When you came in, you would have been handed a feedback form, and we'd really like to ask you to fill that out. We really value the feedback we get. Again, being a grad student-run organization, we really rely on that feedback to improve our operations at these events. Just sort of doing something out of the goodness of your heart isn't enough incentive. We do have to as a little bit more motivation as well. We'll have those after the talk. So we have a great evening ahead. We have a talk, we have observing. I believe we're going to have really good skies tonight, which is pretty rare in Toronto, so hopefully it stays clear. We have some planetarium shows, if you got tickets for those. And we have more things, including refreshments, which I always forget to announce, so I wrote it down in bold. We have food, free snacks upstairs after the talk. And so for tonight, our speaker is Matt Young. He's a fourth-year PhD candidate in astronomy and astrophysics, and he works in the long wavelength lab. He's from Australia, which you'll realize as soon as he starts talking. But in his free time, he enjoys hiking in the great Canadian outdoors. So let's all give Matt a warm applause.
Let's start by saying g'day everyone. So welcome to AstroTours. So is the mic on? We'll find out. Can you hear me at the back? Feel good? So I'm a fourth-year graduate student here at the University of Toronto, and I spend a lot of my time working on a project I love personally, which is the South Pole Telescope. And so tonight I'll tell you a bit about the science behind that telescope, our latest camera that we've just recently upgraded called SPT3G. And I'll take you on a bit of a tour down to the South Pole on the trip I did in November last year, taking down parts for this brand new camera to perform a big upgrade. So when I first was moving to Toronto, I knew I was moving to one of the biggest cities in North America and one that was going to be pretty cold in the winter, but I didn't think it was going to take me somewhere even colder than that, where your breath crunch freezes to your face and a runny nose will freeze instantly. So it's a pretty interesting story about how I got there, and like most interesting stories, it starts in 1964 with two scientists cleaning bird poop off their telescope. So back in 1964, two scientists, Robert Wilson and Arno Panzaius, were working on this experiment, bouncing radio waves off of balloons, very sensitive, and they were trying to remove all sorts of interference from their measurements. So they were doing things like trying to remove telecommunication signals. They were even looking at, like, say, the temperature of their receiver. And they even went to the extent of trying to remove two pigeons that were roosting in the telescope, and in the words of a true scientist, also removing the white dielectric substance that they leave behind. But try as they might, there was still this signal that was there day and night towards the galaxy, away from the galaxy. And looking in more detail, this is what it would look like across the entire sky. This kind of microwave signal from a source that appears to be about 3 Kelvin. So we use Kelvin a lot in astronomy. It's similar to degrees Celsius, you just subtract 273 degrees from it. So they saw this signal everywhere in the sky. And when you see that, I know what you're thinking. That is a Nobel Prize. And they actually won a Nobel Prize for this discovery in 1978, because what they had discovered was the cosmic microwave background. So this remnant radiation that kind of fills all of space from just after the Big Bang. So while this was a major discovery in itself, these days we're less interested in, say, the overall magnitude of that signal, and we're interested in tiny, tiny fluctuations on that. So if we turn up the contrast in this image, we can start to see small variations which are about 1 part in 10 to the 1,000. Sorry, 1 part in 10,000. So this is like looking at centimetre high ripples on a kilometre deep ocean. So very, very small fluctuations. But encoded in these, the red and blue spots there, tell us where the universe was, say, extra dense or under dense just after the Big Bang. So just as a bit of a refresher, because I forget myself sometimes, we have light comes in a huge variety of different flavours, so different wavelengths. We have radio down the large end, so wavelength the size of, say, buildings and people. We've got optical, and I'm sure you've all had an X-ray before. Microwave sits just next to the radio. So microwaves are almost similar to radio waves. If you've ever used a TV where you see static on the screen, some of that static is actually the cosmic microwave background being picked up by the antenna. So, brief history of the universe. Big Bang down this end, us down this end, but all the stuff we know and love. So, after the Big Bang, the universe was hot and dense, pretty much this big soup of everything, and it was opaque. So light was bouncing off everything in it. So as the universe starts to grow, to expand, to cool, we hit a point where the universe shifts from being opaque to being transparent. So all this light that's caught up is allowed to escape and just shoot out throughout the universe. And so locked in at that moment where the light could escape is an imprint of the universe just after the Big Bang. So not only is the cosmic microwave background useful on telling us what these early conditions were like, us today looking at it 13 billion years in the past, it has to travel through all the stuff in the middle. So it's also another important tool for astrophysics, just looking at everything that's passed through in between. So one of the first things people tried to do with the cosmic microwave background was create this thing called a power spectrum. So all those little changes in temperature, we want to know how many, say, big variations there are, how many tiny ones there are, and so we can look at the kind of distribution there is. So this in itself was an extremely powerful measure for cosmology. This can tell us things like the universe is flat, it can tell us what the universe is made up of, the relative fractions of things in the universe, and this is all from just looking at statistics of those tiny, tiny temperature fluctuations. So we've been measuring the microwave sky for a few decades now with many different experiments. So things like COBE, WMAP and Planck, Planck being the last satellite we sent into space to do this. So looking at, say, a little cutout of the microwave sky, we have the Wilkinson microwave anisotropy probe, which went up in 2001, produced images like this, which were fantastic at the time. Fast forward 10 years to Planck, we can start to see a bit more kind of resolution. It just looks like static on a TV screen, but there's a huge amount of science locked up in that image. So this was fantastic as well. Comparing that to an image South Pole Telescope can produce, so using SPT Pole, which was our second camera, even more resolution once again. But the thing that you can start to see these little white and black points popping out from kind of behind that static. So doing some filtering to the image, just so we can see things a bit better, there's still these tiny fluctuations from the CMB. So it turns out those white spots are actually point sources, so far away galaxies, active galactic nuclei spewing out all this radiation that happens to be picked up by our telescope. But even cooler than that, I reckon, are these little black shadows that you can see here. And they are actually clusters of galaxies. So clusters of galaxies being the largest gravitationally bound objects in the universe. This is things that have collapsed to form, stars, galaxies, and then groups of these galaxies. So clusters of galaxies are about 10 to the 15 solar masses. So that's a one with 15 zeros behind it, the largest, almost massive bound objects in the universe. Not only are they massive, but they're also pretty hot. So about 10 million Kelvin. So that's around the central temperature of the sun. But the things that are actually hot is all this gas that's almost in between the galaxies. So these are extremely low density gas where you might have one particle per cubic meter. But even though we call them galaxy clusters, only about 1% of their mass is in the actual galaxies themselves. So what this means is if we go out and look for galaxy clusters just by looking for galaxies, we're going to have a hard time. We're only going to find the ones that are closest to us and are the most massive. So as it turns out, 9% of their mass is made up of this really low density gas between all the galaxies. And this is how we can see that shadow that it leaves in the cosmic microwave background. Does anyone want to have a guess what the other remaining 90% is?
Dark matter.
There you go. So 90% of galaxy clusters, of their mass, is made up of dark matter. And this is what dark matter looks like. So this is one of the biggest outstanding problems in modern astrophysics. We don't exactly know what dark matter is. But we do know a couple of things. We know that it doesn't interact with light and that it does interact gravitationally. So in the case of a galaxy cluster, although we can't see the dark matter, there is so much mass there from the dark matter, it's going to impact that gas, impact the galaxies, so we can use observations of those gas and galaxies to tell us more about this dark matter. So in the case of those shadows in the cosmic microwave background, we have our galaxy cluster with all the hot gas in between the galaxies. We have our cosmic microwave background backlight, which is coming towards us on Earth. As it travels through the galaxy cluster, there's so many of these high energy particles, there's a good chance a few are going to get kicked up, get a bit of an energy boost, which we then see here today in our telescope. So this effect was first theorized in the late 60s, early 70s by two Russian astrophysicists, Sanyev and Zeldovich, and hence we have the Sanyev-Zeldovich effect, which shows, here we have a map of the cosmic microwave background by the Planck satellite. And you can see for a few of the frequencies they're looking at, we see a bit of a shadow there, and for other frequencies we see a bit of a hotspot. So this unique kind of spectral feature that we see allows these microwave telescopes to be awesome galaxy cluster hunters. Even though we're actually looking at the CMB, that's our primary science, we almost get this little bonus of finding all these galaxy clusters. So here we have a couple of surveys showing their mass and distance away from us of galaxy clusters we found using microwave telescopes. We have Planck here, which has found a lot of the really near massive ones. SPT-SC, which is the first camera that we had on the telescope, has found about 500, and SPT-3G, this is a forecast of what we hope to find, thousands of new galaxy clusters, so thousands more than we've ever seen before. So it's a very exciting time for galaxy cluster research. But then the telescope itself, so I'm sure you've all worked out, South Pole Telescope is at the South Pole. It's a 10-meter dish that collects all the light, and we end up usually looking at about 3 different frequencies. So similar to how you might, change the receiver on your radio to pick up like a certain radio station, we have 3 different ones that we're looking at to build the best picture that we can of the microwave sky. So in 2007, the very first camera went down, SPT-SC, which had about 960 detectors. 5 years later, we upgraded to SPT-Pole, the second camera, which had 1,600 detectors, so twice as many. But then just in 2017, we deployed SPT-3G, the one I work on, which has 16,000, so 10 times more detectors than the very last generation. So we're getting more and more sensitive at almost like a runaway pace. So not only that, we have the 3 frequencies we're looking at, and we're also sensitive to polarization of the light, so kind of what angle it's coming in at. So the way this telescope works is we've got our big 10-meter dish, and this collects the light and reflects it down into our camera in this little box here. So inside that box, we actually have 2 more mirrors that the light bounces off, and it heads down into our camera. So although this is a big microwave camera, it actually looks a lot like a gigantic DSLR camera, and it's more or less the same principle. You've got this big cylinder here containing all your lenses that focus the light, and we've got this rectangular box at the back containing all our detectors and electronics that do the processing of the image. So pretty much the same idea, except this one isn't going to fit in your pocket. So we actually do a fair bit of the testing for this camera right here in Toronto. So just in the Astronomy building, in the lab that I work in. So here's me and one of my colleagues, Dr. Tyler Anatoly, testing a part of this camera right here in the lab. And we use a special fridge called a cryostat to get us down to these ultra cold temperatures that the camera operates at. So we'll test different parts and we'll provide feedback to the fabrication process, and we'll kind of tune parameters so the camera is working exactly how we want it to. So although it looks like a gigantic DSLR camera, it works slightly differently to, say, the optical ones that you're probably used to. So we use things called bolometers. So it's pretty much just a very sensitive thermometer. So we've got this thing called an island or some sort of absorber that when the radiation comes in, we want this to heat up as it absorbs that energy. We'll use a thermistor or pretty much a resistor whose resistance changes with temperature to measure its change in temperature, and then we'll have some sort of a thermal bath which brings it back to the original temperature it's at. But probably the coolest thing about this is we use what's called a superconducting transition edge sensor, or TS for short. So I'm sure some of you have heard of superconducting materials. So these are things that at extremely low temperatures, the resistance of electrical current flowing through them pretty much drops to zero. And so at the moment, people that work in superconductors are trying to find things that superconduct at higher and higher temperatures. And if we can never find something that superconducts at, say, room temperature, that would be an absolute game changer. So here with our transition edge sensor, down at very, very low temperatures, about half a degree above absolute zero, we can see it superconducting, and at high temperatures, it's in its normal region. So it's just behaving like a normal resistor. But then we can operate our detectors in this transition region here. So you remember I said we were looking for tiny, tiny changes in temperature. If we have tiny changes in temperature here, we see a huge change in resistance for our detector. So they're perfect for trying to measure these tiny fluctuations in the CMB. So the other thing we need to do is somehow get our light that we're trying to measure onto that detector. So similar to, say, like a radio antenna, we have an antenna that couples the light out of the sky. We then transmit it along a microstrip, possibly filter it, and dump its energy onto a little island there. So just looking at the microwave sky for a second. So here we have, say, like almost signal strength and different frequencies for the microwave sky. So most of the time we're interested in the CMB itself, but then there's all this other stuff emitting microwaves when we're observing. So there's thermal dust from like our galaxy or other galaxies, things that more or less get in the way. So what we can do is instead of picking a single frequency and making a measurement, we can make measurements at many different frequencies to kind of build up that whole picture, and later on we can do some smart things to kind of look at how these all depend on frequency and remove them from the maps of the sky we're making, so we're only left with the thing that we care about. So building that into our design, we can have an antenna that absorbs all these different frequencies. We can then filter some of them out and send them off to their own detectors. So putting this all together, we then have the SPT 3G pixel design. So you can, it's a bit hard to see, but there's a scale there of about 1 millimeter. So this whole thing is probably about 7 or 8 millimeters across. So that funky looking thing in the middle there, that's our antenna. It's also a fractal design, so if you were to keep zooming in, that pattern would just keep repeating and repeating and repeating. So with our antenna, we absorb all the microwave light that we're trying to measure. We then split that off into the 3 frequency bands that we're interested in and send them to their own bolometer transition edge sensors on the side there. So kind of a bit of a different angle. These transition edge sensors, you remember I said they were kind of like an island. You can see that we've etched out all the material underneath them using like a microfabrication process. So they're just suspended there on these really thin legs, so they're able to change their temperature really easily. Zooming out even more, we can see all the pixels kind of sit next to neighbors at a few different orientations. And in the end, all of this is fabricated on these 6-inch silicon wafers. So a lot of this fabrication, or all of it, is done by the collaboration ourselves at Argonne National Laboratories in the US. And so each one of these wafers will have 271 pixels for a total of about 1,500 of those TES detectors on something about this size. And I've actually got one here that you're all welcome to come and have a look at afterwards. The difference being this one has all these white dots on top. So each one of these little pixels has its own little lens on top to help focus the light down. So as we test this, we'll look at the properties of all the different detectors and feed it back into the fabrication, and they might tweak their recipe a bit to kind of get the best possible performing camera part that we want. So the telescope itself ends up having about 10 of these together, tessellated, making up our camera focal plane. So similar to even the camera in your pocket or like a regular DSLR, you'll have some sort of surface that the light is being focused onto, so we can then measure that and make our image. So we've got our camera, but then why bother putting something all the way at the South Pole? Is that better? Yeah. So the South Pole, being roughly in the center of Antarctica, Antarctica is a huge continent. It's about 1.5 times the size of Canada. I did not realize just how gigantic that is. So one of the benefits of having such a gigantic continent with very, very few people there is people are far away. So similar to telescopes, radio telescopes, people, all the signals from cell phones and everything else in computers just ruin the measurements you're trying to do. So here we're really diminishing the human impact we have on the measurements we're trying to make. But an even better reason is the cross-section of Antarctica. So Antarctica is still a continent. There is still the land mass beneath, but most of it is buried under kilometers of frozen water. So the South Pole itself is actually at 3 kilometers above sea level, so decently up there. And so similar to many other optical telescopes or other ones, we like to put them at the top of tall mountains, right? Because we want to get above the atmosphere. So the atmosphere has lots of turbulence, it's always changing, and more or less we like to, we love to put telescopes in space, even better, because we're away from all that atmosphere. But the next best thing we can do, if we're not going into space, is get as high up as we can. So this is a good start, but then we've got plenty of other mountains. Why this one that's so far away? And the third reason is this. So it's the way your microwave oven works. So you put your food or your drink into your microwave oven will then start generating microwaves that get absorbed by the water molecules in your food or your drink, and so that heats it up. The same thing actually happens in our atmosphere, right? We've got the cosmic microwave background coming to us from outer space. It'll hit our atmosphere, which has lots of water vapor in it, and be absorbed by that water vapor, so we can't measure it. Luckily for us, at the South Pole, all that water vapor isn't in the air, it's frozen right beneath your feet. Because the South Pole and Antarctica, for the most part, is actually a desert. There is close to 0 rainfall or snow, at least at the South Pole. So this means we're not absorbing too much of ours by the atmosphere. And if we look at, say, our frequency bands that we're trying to measure, so these are the 3 little windows that the South Pole telescope looks at in the microwave. In the black, we have what's being absorbed by the atmosphere. So we have these nice little windows we can look through the atmosphere out into the universe with. If we were to make a similar plot in Toronto, there's no chance we could see that kind of level. And there's also another benefit on top of that, which is the sun rises and sets once a year at the South Pole. There are 6 months of the year where the sun is above the horizon and 6 months of the year while the sun is below the horizon. And once it dips below the horizon, you end up with a little period of twilight as well. So whenever the sun is rising and setting, it's heating and cooling the atmosphere. And when you're heating and cooling the atmosphere, you can end up with lots of turbulence. So because we only have one sunrise and one sunset, we end up with a fairly stable atmosphere at the South Pole as well. But in this, we have our biggest trade-off. We can only get to the South Pole for 3 months of the year. From about February all the way through to November, it's too dangerous to fly anywhere near it. It is too cold, it is too windy, no one will do it. So what this means is every year, a lot of the scientific experiments will get their team together, madly rush down in November and try and squeeze in a year's worth of work in 3 months, doing any upgrades you need in time to make this last flight out before being stuck there for another 9 months. And there is actually a team of crazy people that will stay there for that 9 months through the winter, keeping the station and the telescopes running. So in November last year, I was lucky to be part of the crew for SPT, heading down with our latest and greatest upgraded parts for the camera. And so I jumped on a plane here, headed through LA, New Zealand to McMurdo on the coast, and then onto the South Pole. So our first stop was Christchurch, where we picked up a lot of our cold weather gear. So a lot of the US Antarctic operations are based out of Christchurch. We pick up our big red jacket, affectionately called a Big Red. The big red jackets are actually made by Canada Goose, which is why they all have the little patches that either say Antarctic or Arctic or Antarctic program. We picked up our big boots and bunny boots. All of this is required to be worn on all flights in and out the continent. So we picked up our stuff. We were due to fly out the next day, so we get up at 5 a.m, check out the hotel, wait for our bus, and we get a call saying, plane's not going. So we go and sit in a coffee shop for the rest of the day, check back into the hotel. Next morning we get up at 5 a.m, check out the hotel, get a call, plane's not going. This happened 6 days in a row. And you can tell how horrible it would be to be stuck in Christchurch for 6 days. But finally, the New Zealand Air Force was nice enough to give us a lift down. So we all got on one of their 737s, which was gunmetal grey on the outside, but looks like a regular airliner on the inside. And we even had the New Zealand Air Force people wheeling trolleys down the aisle, handing out tea and coffee while wearing their full military camouflage gear. So that was interesting as well. So we took off from the tarmac and then landed on a very different type of runway, about 10 metres of frozen sea ice just outside McMurdo. So once we landed, we all piled in our little transport that then took us onto McMurdo, which is the biggest base on the Antarctic continent. So this is a US base. There's about 800 people there during the summer doing a huge array of different science experiments on the wildlife and even people to just keep the station running. So while we were here, we didn't have a whole lot to do. The internet there is a bit slow. We're due to go onto the South Pole as soon as we can. So to keep ourselves busy, we wait for our flight. And you only know your flight is about to leave due to these little screens around the station they call the scroll. And so it'll say your flight's due to depart in 2 hours. And then you'll get a few minutes out and it will be delayed by 2 more hours. And a few minutes out and delayed. So you really just have to sit around this whole day waiting on your flight that will maybe possibly leave. And you can see delayed, delayed, delayed. So after a week of watching these screens update over and over, you can see you start to lose your mind a little bit. But finally, the stars aligned and we could get on our plane that would take us onto the South Pole. So a lot of the bases are serviced by these old military aircraft from the 60s. This is called an LC-130. So on the inside, you all pile in and sit on these red netting seats. You have knee-to-knee or knee interlocking in the case of the tall people, so I don't think I'll ever complain about legroom again on the flight. And although it was a bit crammed, we were free to get up and wander around and look out these little portholes on the side where we could see, at least at the start, the mountains, and then the glaciers between the mountain would just get higher and higher and higher and higher until when you step out at the South Pole, what do you see? Well, not a lot. It is flat white snow as far as the eye can see in every single direction. So over to the left, we have the telescopes, which I'll come to in a bit. And I'm just walking around the corner towards the Amundsen Scott South Pole Station, which is over here. So the South Pole Station is named after Amundsen and Scott, the first two explorers to make it to the South Pole in the early 1900s. And this is in the third iteration of the South Pole Station after the US claimed the South Pole for themselves in the 50s, as they like to do. So this last one was built, I think, about 10 or 15 years ago. And it's actually on stilts, with the idea being that as the snow level changes, they'll be able to raise it in the future, hopefully prolonging its lifespan. So about 150 people live and work in this building over the summer. Everyone sleeps there, everyone eats in the galley there. We get about 4 hours of internet a day as the satellite happens to go over the top, 8 if you're lucky when another satellite is playing nice. One of the first things I noticed though was due to the really high altitude and the dryness of the air is you kind of lose your sense of smell, which is just as well because you get 4 minutes of shower time a week. Usually you'll split it into 2 2-minute showers just if you're being nice for yourself. So luckily you couldn't smell a whole lot, which I think works for everyone. So just over here, a bit hard to see, we have the actual geographic South Pole. So this marks the point where the Earth rotates around and that gets moved in a special ceremony every New Year's Day, shifting about 10 meters due to continental drift. And then over here, we have the ceremonial South Pole, which is for all the photo opportunities. And this is my supervisor's first instruction, get a South Pole selfie. So being the good student I am, I happily obliged. I think this was after I managed to drag myself out of bed on the second day after having some fun altitude sickness. So usually when you're going to these altitudes, you'll either be hiking or driving up. In our case, it's just the plane takes you from sea level and drops you at high altitude. So it can take a little while to adjust. And from here, you can turn around and see the station behind. So from the station, where we were working every day was actually about 1 kilometre down the road called the dark sector. So the dark sector pretty much meant radios were prohibited just because they interfere with the experiments. There's also a few other scientific specific regions. So over to the left here, there's a place called the clean air sector, which is just always upwind from the station, so it's not getting any contaminants. So in the dark sector, we have 2 other microwave telescopes, Keck and Bicep, that you might have heard of. South Pole Telescope, and there's even one called Ice Cube, which is a neutrino observatory. So they have all these holes drilled throughout the plateau, kilometres deep, trying to detect these elusive particles. So every day we would walk out to the telescope. It took us, it's maybe a 10-minute walk, and we do it about 6 times a day, usually after breakfast, lunch and dinner. And no roads to cross, but we do have to cross the runway. And you can see there's a sign here saying, wait here while crossing beacon is flashing. So every now and then we'd have to stop and wait for a plane to land, and even when this wasn't flashing, you would want to look both ways, because believe it or not, there have been close calls of people almost walking in front of the plane. So it was pretty awesome being able to see the telescope for the first time, seeing as I've been working on this for years, sending all these parts down. To actually see it for myself was a pretty cool experience. So in order to do the upgrades we needed to do, you remember that the camera is sitting here, we need to get it out of the actual telescope itself. So this is a time lapse, so it's sped up a bit, but the telescope can actually dock with the building, and you can see we pretty much just open up the roof of the building and swing it around so we can start accessing the camera inside. And just to give you a sense of scale, there's 2 people cleaning snow off the dish. So once that was docked with the building, we could start lowering the camera out, and this was several hours on this time lapse, slowly jiggling it down, seeing as the camera was about the size of the opening we had to get it out of. So once we had the camera down on the ground in its own special rack, we could start taking everything apart. So we ended up pretty much completely deassembling and reassembling the entire camera twice, because not only did we have to replace all these lenses, so we replaced the lenses, did a test cool down with it, opened it up all again to make sure they're fine, and then close it up again. While this is going on, we're also, me and another grad student, were assembling these detectors that we have with all the readout electronics that sit on the back. So pretty much exactly what I do in the lab here in Toronto, the only difference being that these ones are definitely going in the actual telescope, and if you break them, you'll be leaving a very unpopular person. So here we have the rear side of 10 of them coming together, and it really is a bit like a gigantic Lego set. There's not so much the explicit instructions, but everything fits together in a very purposeful way, so it's quite fun to screw everything together. So once we had the focal plane assembled, we installed it in the back of the camera, and it looks like a bit of a spaghetti mess of cables there, but this took 2 people several days to cable everything up, making sure none of these were touching anything that they shouldn't be touching. Looking at the other side, we can see that the hexagon shapes of our detectors there, all 10 of them, almost like you're ready to screw the lenses on and close it up. So that's exactly what we did. We put everything back together, and we were ready to start testing things on the ground before we could put it back in the telescope. So taking inspiration from some of the best construction crews in the world, we realised testing goes a lot faster with 1 person working and 7 people watching. So once everything was working, we knew things were behaving as they should. We pretty much reversed the process of hoisting it back up into the telescope and start doing tests on the sky with actual microwave sources. So most optical telescopes or other types of things will pick a spot in the sky, and they'll stare at it and stare and stare and stare, because you want to build up as much light as possible. In the case of our microwave telescope, we're using those bolometers that pick up the changes in temperature. So what we do is we scan backwards and forwards, and as we're scanning through the patch of the sky we're observing, we pick up those changes in the temperature as we're going backwards and forwards. And worth pointing out, this is again a time lapse, so it's sped up by about 20 times or so. There's about 30 seconds between each time it changes directions there. So it was a pretty full-on couple of weeks trying to get everything upgraded in time, seeing as we rocked up 2 weeks late, not our fault, but lots of rushing getting things done. We didn't really have too much time to relax, but once things looked to be working, we did have time to let down our hair, especially when the satellite isn't up with the internet. So especially to keep people entertained over the long winter as well, there's actually quite a few facilities they have there. They have a decently stocked band room. They've got a full-on gymnasium with a weight room. They have people play weekly basketball games and badminton games. And they've even got a sauna. And so one of the best things about a sauna at the South Pole is when you get too hot, you can cool off outside. And people are actually crazy enough to do this in the middle of winter. They have a thing called the 300 Club, where they'll turn the sauna up to 200 degrees Fahrenheit. And once the temperature hits minus 100 outside, they'll go and run around the South Pole. Wearing less clothes, I should add as well. So as well as that, we had, say, like a Christmas Eve dinner, a New Year's Eve celebration, and we even had a thing called the Race Around the World on Christmas Day. So this was a 4-kilometre race around the South Pole, covering all 360 degrees of longitude, where the winner got the grand prize of 10 minutes shower time. So really living like a king there. So speaking of going on runs, one of the things I did like to do was go on a run on this little track that took me just past the telescope, where pretty much the road ends and there is nothing that humans have touched for thousands of kilometres. So it really gives you an idea of just how isolated you are at this spot at the end of the world. And one of the things people like to point out is it's actually quicker and easier to rescue someone from the International Space Station than it is to rescue someone from the South Pole. So that was the day when you can see the horizon. There was days when you can't see the horizon. So when it becomes a bit overcast, the snow really just mixes in with the sky and buildings seem to just kind of float out there in the distance. Days when it wasn't too overcast, we were sometimes lucky enough to get these things called sundogs. So this is ice crystals in the sky that form these huge rainbow halos around the sun. And on some days they'd even kind of branch off, forming even more halos to the side. And talking about weather, this is one of the photos I took of the dark sector laboratory where our telescope is. And just take note that the snow level, we can walk into this door here. So this is a photo my supervisor took 10 years ago over the winter. You can see in about 10 years, the entire snow plateau has risen about an entire floor. And you might remember I said that it doesn't snow at the South Pole, and it doesn't. All this snow is called snowdrift. So it just pretty much blows across the continent and will bury anything that's left there without human intervention. So even the original South Pole station built in the 50s was buried after about 10 years. And that pretty much sat there buried under meters of snow until they blew it up with TNT about 5 years back, because people were sneaking in the middle of winter and they didn't want that to be happening. But yeah, this snow just keeps building up, and eventually buildings have to be deassembled, taken apart, because you just can't fight against that force of nature. So after 2 months of calling this weird and wonderful place home, it was almost time to leave. Though similar story to the start, we never knew if the plane was coming or not. So our final days really involved sitting in the galley, stoking the rumour mill as to whether the flight would come in or not. And the funny thing is the fact that you don't really have the internet a lot of the time. The entire station really does run on a rumour mill. There's all this gossip that goes around to kind of keep people informed. And this was one of my favourite weather reports in the last few days waiting for our flight. This last line here: no flights today, probably, most likely. So after a week, a plane landed, which was pretty exciting. After a few false alarms, a few planes made it halfway, and they'd have to do what's called boomeranging. They'd turn back for whatever reason. But finally, the plane came that was going to take us home through McMurdo, through Christchurch, and then back to North America. And so, how's that for a departure lounge with a view? So I left middle of January. The station was open for about another month for the rest of summer, with a few other team members there finishing off jobs, where we left the station in the capable hands of our winter rovers. So the whole station has about 40 people there over the winter, with 2 of those people working on the South Pole telescope. So the rest of the photos I'm going to show you are ones taken by our winter rovers this year. So this shows just the sun going down to start the very long night. And even though they missed out on seeing the sun most days, they do get treated to some pretty spectacular auroras. And there's even a few photos where you can just see the whole Milky Way as well stretching over them. So pretty lucky to see that. But they worked away super hard all year, kept the telescope running in some of the craziest conditions that I know of. And then just 2 weeks ago, the sun has started to poke its head up above the horizon, starting a new day, a new summer, which I'll actually be heading down in less than a month again. Another round of upgrades, so taking down these new and improved detectors that we've been working on this year. And yeah, excited to head back down. And I'll leave you with the very last photo that our winter rover sent up just yesterday. So now the sun is finally up. Things are looking a fair bit more frosty than when I saw it last, but yeah, looking forward to going down and doing some more astronomy at the end of the world. Thank you.
Thank you. We have time for some questions, so I'll just ask when someone
and ask anything about the science, the telescope, Antarctica, anything at all.
So in that time-lapse video, I noticed that the sun was sort of staying in the same spot, it didn't track. I get that seasons and all that has to do with tilt of the Earth, but the Earth's still spinning, so why is it when you're at the South Pole, the sun just sort of hangs in one spot instead of circling around?
So it actually does exactly that. So the question was about the sun in the time-lapse staying in place. And so that was actually a bit of a small section of a time-lapse I took. In the entire video, if you watch for long enough, you can see the sun go around. So the whole time I was there, the sun is up. The sun just circles above you over and over and over. The best you can probably do is tell what time it is based on the direction of the shadows. So the question was about the use of hexagons in telescopes and that kind of stuff. I think the easiest thing is they tessellate well. If you're using circles, you end up with all these spots where you can't really have detectors. Hexagons are still making the most of the room, and you're still picking up as much as possible. I think that's really why they use it.
Are there any plans to integrate gravitational waves into how the South Pole telescope functions?
The question was about integrating gravitational waves into how the telescope functions. There isn't, but if anyone comes up with an awesome idea, I'm on board.
Who won the 10-minute shower race?
Well, sadly not me, but then one of the people in SPT won second prize, which is 5 minutes of showering. So
I see, of course, there's like all the lights and all that. How do you get all the utilities for the base, like the electricity, the water?
So electricity, there's pretty much they burn jet fuel is the simple answer, and you actually find you lose your sense of smell, but the only thing you can smell if you try hard enough is just this lingering sense of jet fuel everywhere. But for the water, they actually have a thing called a rod well. So this is pretty much they pump hot water down into the ground to melt more hot water and then bring it back up, which, as it turns out, is a very energy-intensive process, which is why you have to treat water as such a special resource. Right at the back.
Does the aurora affect the telescope's results?
So the question was if the auroras affect the telescope results. The answer is luckily not really. So I'm sure it would have a bit of an effect that kind of mixes in with the atmosphere, but we have some pretty good techniques in terms of removing signals from the atmosphere, so it doesn't really. So the people there in the winter can just sit back and enjoy it.
You mentioned that if superconductors were at higher temperatures, it would be transformative. Why is that?
So the question was about superconductors being at room temperature and they'll be transformative. So whenever we transmit electricity, there's a cost to it. We need to force that through different wires that have a resistance. So superconductors being zero resistance whatsoever, you could almost look at it as transmitting electricity for free. I don't know if we'd ever get to room temperature, but as that kind of floor comes up, there's a lot more uses we can find for them.
So what are some of those uses?
I can't think of any off the top of my head, sorry. Better telescopes.
But it would lead to better.
Yeah, definitely, and that's a very active field at the moment in terms of superconductors.
You mentioned you cool the detectors. Do you actually have to cool them there? Like, do you have like liquid helium or something there?
So we do have liquid helium. So there's a few different cooling systems that we use. We think so most things are at room temperature, which is 300 Kelvin. We have things called helium pulse tube compressors, which use this kind of trick you do with helium to get it down to 50 Kelvin and 4 Kelvin. And from there we use liquid cryogens like liquid helium to get us down to sub-Kelvin temperatures.
Your new detectors, what factor improvement are you expecting?
So one of the factors we use to kind of measure how good these are is a thing called mapping speed. So it's almost like how often you would have to revisit a patch of sky to get the same result. And our new detectors, we're predicting, if everything works perfectly, a mapping speed improvement of 20 times. So that means we could observe a patch of sky or 20 times faster, more or less, to get the same results as before. So the question was, does it rain in Antarctica? I'm not sure at the coasts specifically, but for most of the continent, there is close to zero rain or snow. And you might have heard before people call Antarctica a desert, because by desert standards, it's below a certain amount of rainfall every year. So yeah, very little to no rainfall in most of the continent.
How expensive are each of those wafers?
Priceless. So it's one of those things we actually face when we have to ship them between collaborations, especially over the US border. You have to put a price on things, right? But for a lot of it, it's fabricated in-house by the collaboration. It's months of work on someone's behalf. So they're almost, each one's like a one-of-a-kind device. So probably many thousands of dollars in terms of someone's man hours or people hours putting it together.
What do you hope to find from your research or figure out?
So me personally, the thing I love most is being in the lab just screwing things together. But then me personally, in terms of the research, I do a lot of stuff on galaxy clusters. So as I said, we're finding heaps more and more at higher distances. So we're now reaching a point where we can actually look at kind of the profile and distribution of this gas in some of the furthest away, most light galaxy clusters. And that should hopefully give us a better idea of how these start to grow and form in the cosmic web.
So time for just a couple more questions for the room, and I will still be around afterwards while we're moving on to the next portion.
Why were fractals chosen to be the antenna in the sensor?
So the question was, why were fractals chosen to be the antenna? And so I'm not sure, like some of the classic kind of radio antennas that have all the little rods at different lengths. So we want to absorb different lengths of light. So with that fractal design, as you zoom in, you can kind of find all those lengths of antenna as you move towards the center. So that allows us to receive a huge chunk of that spectrum.
What's the best and worst parts of your PhD or your job?
The best and worst parts. So I'd say the best is probably being lucky enough to do trips like this. The worst part is, I don't know, I find that you're usually always thinking about these problems that you're coming across. So it's hard to kind of leave the job at work, but that can sometimes be quite rewarding in itself sometimes.
Okay, so I'll just ask for a few more moments of your patience. Do you have the post slide?
Yes, I do.
Okay. Should pop it up. So one thing is we have a huge group of volunteers. Here, I'll turn my mic on. So we have everyone here. There's a big group of volunteers who are working on things from the telescopes that we have for observing and for planetarium ambassadors as well. So if you got planetarium tickets beforehand, we have two ambassadors. We have Hannah and Emily, who you will meet at the meet point, which we recently had on our map. It's right in front of the elevators, and the elevators go up to where the telescopes and a lot of our other activities are. We have observing, I believe it's still clear out. The forecast was for it to be absolutely clear, good, dark skies, finally for once. We have refreshments upstairs. We also have an Oculus Rift. We have 3D printed telescopes. It's awesome. And also for your feedback forms, again, if you don't have pencils or any writing utensils, we have some up here, and we'll take them. We also have the cookies. And so before we move on to the next portion of our evening, let's all thank Matt one more time.